to have provided such wonderful technology through which we can enjoy the subject in a multifold manner. So, we are now trying to solve some nice problems based on what we could understand in solid state chemistry. So, let us continue the journey with problems. See, yesterday we have done this. How many nearest triangular voids are present around an octahedral void? This we have done. See, at the octahedral void in a face centered cubic unit cell is at the center, and towards every corner there is a triangular void. There are 4 body diagonals, and each body diagonal you will have 2 triangular voids. Therefore, around the central octahedral void there are 8 triangular voids present. The answer for this question is 8, we have discussed. Coming to the next question, what is the volume of HCP unit cell? This also we had a wonderful talk on this. See, FCC and HCP have same packing efficiency. If you take one FCC unit cell, it has got 4 atoms. So, the volume of 4 atoms is 20 units. With the same packing efficiency, volume of 6 atoms in HCP unit cell will be how much? So, we got 30 for this. Coming to the next question also we have done. The oxide ore A plus tetrahedral voids are occupied by A, B, whatever is there. So, we could get the formula of the compound, and we want to prepare 500 ml solution with some B concentration to be 0.02 m. So, based on that we calculated how many unit cells are to be dissolved in the previous lecture. Now, what is the number of unit cell present in 2.34 milligrams of sodium chloride? The sodium chloride unit cell, one unit cell is 4 formula units, NaCl 4 into 23 plus 4 into 35.5. So, we have got 234 gram, 34 AMU. So, that is the mass of one unit cell of sodium chloride. So, if you take 1 mole unit cells, would be having 234 grams. So, we know that 234 grams means Avogadro number of unit cells. How many grams he gave? 2.34 into 10 power minus 3 grams. How much? So, this by this into Avogadro number. So, 2.34 into 10 power minus 3 by 234 into 6 into 10 power 23. So, this goes 100 times, this goes 10 power minus 5 times. So, 6 into 10 power, sorry, answer is 6 into 10 to the power of 18 unit cells. This is based on the mass of a unit cell. How to calculate the mass of a unit cell? Just know how many atoms are spread in the unit cell. You know the atomic masses or ionic masses. Just get the mass of unit cell. Using that, any stoichiometric problem can be solved. So, let us switch over to the next question. What is the nearest cation-cation distance in zinc sulphide structure if the nearest anion-anion distance is 4 angstroms? This also we have done, like this is zinc sulphide, the sulphide unit cell, and you all know these are sulphides. On each corner and on each face you have sulphide ion. Nearest cation distance, but this is sulphide, and he gave nearest anion distance. Where is anion? This is sulphide. What is the nearest anion? The face ion. So, he gave nearest anion distance. If you write the face, this face outside, you are getting this. This is the nearest anion distance. He gave that. He gave that nearest anion distance as 4 angstrom units. Means what? If this distance is 4 angstroms, this distance is 8 angstroms. Nearest anion distance is 4 angstroms. So, complete face diagonal distance 8 angstroms. What is face diagonal? Root 2 of A, edge length into root 2, because this is A, this is A. So, this will be, as per Pythagoras theorem, this will be root 2A. That root 2A happens to be 8 angstroms. So, what is A? 8 by root 2. That gives me 2 into 4, 4 root 2 angstrom. Remember this, remember this. Now, what is asked? Nearest cation distance. So, where are the cations present? Zinc ions, they are present in the alternate tetrahedral voids, means they will be inside the cube. Alternate tetrahedral void means if you draw one more cube inside like this, see, these are all tetrahedral voids, but alternate tetrahedral voids are occupied. So, only these are zincs. See, this the red spheres are zinc ions, alternate tetrahedral voids. Now, we want this distance, nearest cation distance, means what? It is the face diagonal of the inner cube. If you add up all the tetrahedral voids in a face centered cubic unit cell, this is a wonderful information. You will get another cube. What are the measurements of that cube? Very simple. See, this tetrahedral void is at 1/4 distance from the corner on the body diagonal. This is also 1/4 distance from the body diagonal, means this body diagonal of the inner cube will be what? Half of the body diagonal of the outer cube, because 1/4 is cut here, 1/4 is cut here, and this will be half of the body diagonal. So, this will be what? Root 3A by 2, because the total body diagonal is root 3A, we want only half of it, it will be root 3A by 2. So, immediately what will you understand? What is the edge length of this cube? Once the body diagonal is root 3A by 2, what do you understand? Edge length of this inner cube will be A by 2. If the edge length of the inner cube is A by 2, what will be the face diagonal? If edge length is A by 2, face diagonal will be root 2 times of that. So, the nearest cation distance will be root 2 of the edge length. So, root 2 into edge length is A by 2, that gives me A by root 2. So, the nearest cation distance will be A by root 2, but what is A? We have already proved 4 root 2. So, what is the cation distance? 4 root 2 is A by root 2, it is going to be 4 angstroms. So, in zinc sulphide structure, nearest anion distance, nearest cation distance are also same. That is a beautiful question. So, you can work out like this, simple mathematical approach. In a rock salt like structure, what is the percentage occupancy, assuming the cations exactly fit in the voids of the anions? Very simple logic. See, actually in any, it is an FCC lattice, rock salt means what? FCC lattice. he says the spheres are exactly as per our hard spheres close packing. So, in this 74% is the effective occupancy of the spheres. In addition to this, even the cations have joined the octahedral voids. So, each octahedral void is filled with exactly fit cation. So, you can assume that all the octahedral voids are occupied. And what is the radius of an octahedral void? We have already done 0.414 capital R. R is the effective radius. So, there are 4 cations present per unit cell. And what is the volume for this radius? 4 by 3 cation volume. Volume of cation 4 by 3 pi radius of cation 0.414 R cube, and this is the volume of cation. How many cations do we have in rock salt unit cell? 4 cations, because at the body center and each edge length. So, there are 4 cations. So, 4 into 4 by 3 pi 0.414 cube R cube, 4 times divided by volume of the unit cell. Volume of unit cell is edge length cube, edge length is 2 root 2 R. So, 2 root 2 cube R cube. So, R cube cancel, and you are going to get whatever is the answer for this, 4 into 4 by 3 into pi 0.4 approximate cube by this is 16 root 2. 16 get cancelled. So, you are going to get some value, some x. What is this x? Fraction of space occupied by only cations. The fraction of space occupied by the anions with effective radius is going to be 0.74. So, 0.74 plus whatever value you get here, and that is going to be the percentage occupancy. Into 100 will give percentage occupancy. This is a beautiful question based on considering the octahedral void filling also, right. In an alloy, A forms HCP lattice, atoms of B occupy 2/3 of octahedral voids, C atoms occupy 1/3 of tetrahedral voids. So, basically it is an alloy of A. A is there, B is there, C is there. A is forming HCP, means n atoms of A is forming HCP. Atoms of B occupy 2/3 of octahedral voids. How many octahedral voids will be there? N. Out of n, only 2/3 are occupied. So, 2n by 3. And how many tetrahedral voids will be there? 2n tetrahedral voids, and you have got 1/3 of tetrahedral voids occupied. So, in 2n 1/3 are occupied. So, again 2n by 3, and if you take the ratio, n get cancelled, 1 is to 2 by 3 is to 2 by 3, and if I multiply with 3 I will be getting 3 is to 2 is to 2. So, what is the formula of the Li? A3, B2, C2. He wants the percentage composition of A. Percentage composition of A. So, what is the atomic number of A? 120. How many A's are there? 3. So, its mass is 360. There are 2 B's, 160. There are 2 C's, 120. So, 360 plus and 280 makes 640. But he is asking the percentage of A. So, 360 by 640 into 100, 0 get cancelled, and whatever value you get there. So, as simple as this. This you can calculate provided you have got that knowledge of number of voids, number of tetrahedral voids, number of octahedral voids like questions. 6.023 into 10 power 21 FCC unit cells of sodium fluoride are dissolved to make 400 ml solution. What is the pH of the solution if Ka of HF is 10 power minus 6? This is a question that bridges solid state as well as ionic equilibrium. So, 6.0 10 power 21 unit cells are there. So, how many moles? This many unit cells, be careful, that many unit cells divided by 6.023 into 10 power 23, that gives me 10 power minus 2 unit cells. But sodium fluoride adopts rock salt structure, and we know 1 mole, 1 unit cell is 4 formula units. 1 unit cell is 4 formula units. 1 mole unit cells is 4 moles of rock salt. 4 moles of rock salt. How many unit cells do you have? 10 power minus 2. So, 10 power minus 2 into 4 moles of sodium fluoride is present. Now, that much sodium chloride is dissolved in 400 ml. So, what will be the molarity or normality? 4 into 10 to the power of minus 2 by 400 ml means 0.4. So, this gives me 10 to the power of minus 1. So, finally, what we could understand, the sodium fluoride concentration solution is 10 power minus 1 molar. He is asking pH of this. So, sodium fluoride, Na plus fluoride minus. As we all know, sodium plus cannot undergo hydrolysis. Then who will undergo hydrolysis? Fluoride. So, fluoride plus water gives HF plus OH minus. And what is the concentration of fluoride we have obtained in the previous discussion? 10 power minus 1 means 0.1. So, 0.1 into 1 minus hydrolysis constant, 0.1 into H, 0.1 into H. So, 0.1 into H into 0.1 into H by 0.1 into 1 minus H is equal to the equilibrium constant of this. Equilibrium constant of this is nothing but hydrolysis constant, which is nothing but anionic hydrolysis constant means Kb of fluoride. What did he give? Ka of HF. How Ka and Kb are related? Once you have a conjugate acid base pair, Ka and Kb will be 10 to the power of minus 14 at 25 degrees. Let us assume 25 degrees, 10 to the power of minus 14 by 10 to the power of minus 6. And because HF equilibrium constant is 10 power minus 6, hydrolysis constant will be 10 to the power of minus 8, which is a very small value. So, I can in n minus 1 minus H, I can ignore H value and call it as 1. So, what am I going to get? 10 power minus 8 is equal to 0.1, 0.1 cancel, 0.1 H square. So, H square is equal to 10 to the power of minus 7, 10 to the power of minus 7. So, H is equal to square root of 10 to the power of minus 7, and we want OH concentration, that is 0.1 H. So, OH concentration is equal to 0.1 into root 10 to the power of minus 7. I can call it root of 10 to the power of minus 9. So, POH will be 4.5, negative logarithm of 10 power minus 9. If POH is 4.5, what will be pH? 9.5. So, the answer is 9.5. A beautiful question connecting the number of formula units per unit cell, and the pH calculation. So, there are so many things involved. Simply unit cell molarity, number of moles of unit cell is not number of moles of the salt, because one unit cell is 4 formula units of the salt. So, you have got 10 power minus 2 unit cells, 2 in 10 power minus 2 into 4 is the formula units, divided by volume will give the actual concentration of fluoride ions. See this, the formula weight of A plus B salt is 60.23. If it adopts rock salt structure with the unit cell of edge length 4 angstroms and 5 grams per cc density, what is the percentage of pairs of ions missing in the lattice? This is a very interesting question. He gave you molecular weight. He said it is rock salt structure, means you know how many pairs are there in the unit cell, and he gave the edge length also, from which you can calculate volume of the unit cell also, and he also gave interestingly the density also. He gave number of atoms, he gave molar mass, and he gave the edge of unit cell, then a density also he gave. Then what will you find? So, immediately you should understand this must be, there must be some deviation. Why did he give the density? So, there must be some expected density. So, what is the expected density using this data? Edge length is given, everything is given. What is the formula for density? Number of formula units 4, if the crystal is healthy, 4 into molar mass by Avogadro number into edge length cube, this is in angstroms, 4 into 10 power minus 8 cube, like this. So, what are you going to get? This goes 10 times. So, 4 into 10 by, this is 64 into 10 to the power of minus 1. So, this gives me 400 by 64. This is nothing but 6.25 grams per cc, because this is 100 by 16. 25 by 4, 6.25 grams expected mass, sorry, expected density. But what is the density given in the problem? 5. So, expected density is this much, density given is less. So, what is the difference? Loss in density, 6.25 minus 5, 1.25, that is the density loss. Loss is because of missing pairs of ions missing. How much loss is there? 1.25, out of how much? 6.25. So, percentage loss 1.25 by 6.25 into 100. This goes 5 times, this goes 20 times. So, 20% ions are missing. A beautiful problem. It is not a perfect crystal. So, some ions are missing, so some density is lost. So, is there any other way you can work out this problem? Actually, we can think the other way. He himself is telling some ions are missing. So, why should you take then 4 here? When some ions are missing, why should you take it 4? Let us say some other number, some unknown number. So, we will find out that number using this density, defective crystal density. Then from that particular number we will find out the percentage loss. So, that way also we will try. So, I will take 5 grams per cc density, what he gave. I do not know how many atoms are there for unit cell, I will keep it theta. Theta is effective number of atoms, I mean ion pairs present per unit cell. 60.23 by 6.023 into 10 power 23 into edge length is 4. So, 64 into 10 to the power of minus 24 cc. 1 angstrom is 10 power minus 8 cc cube. So, what would I get? I will cancel it out 10. So, theta into this goes up 10 by 64. So, theta is equal to 5 into 64 by 10. This goes 5 times, I think this is 66.4. So, I will be getting 3.2. Theta into 60.23, this is 60, 10 power 23, it will go 100, sorry, this is 100. So, this is going to give me 3.2, this calculation, this goes 20 times. So, theta I got as 3.2. What is the expected number of ion pairs? 4, no? So, how much I got? 3.2. How much is missing? 4.0 minus 3.2, 0.8. So, 0.8 formula units are missing out of 4 formula units. So, what is the percentage? 0.8 by 4 into 100. This goes 0.2 times, I am going to get 20%. So, two different ways. We took the ideal density missing we calculated, from there we got percentage of ions missing, or we got the given density and we calculated number of effective formula units per unit cell, and ideal unit cell should have 4, the missing ions we found. What is the distance between two vertically aligned spheres? Read the question carefully, a fantastic question, very good question. What is the distance between two vertically aligned spheres in the first and fourth layer in CCP arrangement if the radius of each sphere is 4 angstroms? Vertically aligned spheres, where? In CCP arrangement, first layer and fourth layer. So, what is CCP arrangement? This is CCP arrangement. So, we call this arrangement as CCP arrangement. A, B, C, A layer, B layer, C layer, A layer. He is asking two vertically aligned spheres in the first and fourth layer, means this layer and this layer you select, vertically aligned. So, this is aligned to this, or middle one is aligned to this, or this is aligned to this. All the heights are same, no, from one layer to the other layer. So, he is asking this distance. So, this height is asked. How to work out that? One data is only given. The radius of each sphere is 4 angstroms. The sphere radius, this is 4 angstroms. Only that much is given. So, how to work out this? A very smart way of solving this problem is, let us correlate this particular arrangement with reference to the unit cell of the system, and this being A, B, C, A, B, C means what? CCP arrangement, and this is not the unit cell. I told you clearly, For this the unit cell is FCC unit cell. So, let us first draw FCC unit cell and let us try to find out where these two spheres will appear in the unit cell. So, we will do that. So, this is FCC unit cell. And most of you must be knowing, in an FCC unit cell the adjacent face center atoms are in contact. Adjacent face center atoms are in contact. So, from that what can you say? This sphere and this sphere are in contact, which makes a triangle. A triangular layer you can feel. And the top sphere, back sphere and left face sphere also are in contact. And what is the place present here is the tetrahedral void between those three spheres, and the corner sphere make a tetrahedral void in between. And what is this place? It is a space sandwiched between two oppositely oriented triangular spheres. And next to that again you have one tetrahedral void. So, if you travel this way, what are you coming across? One sphere, one tetrahedral void, one triangular void, one octahedral void, one triangular void, one tetrahedral void, one sphere. So, if you connect this sphere and this sphere, you will be getting this height. Why? Sphere, tetrahedral void, triangular void, octahedral void, triangular void, tetrahedral void and a sphere. So, A, B, C, A. So, this line is A, this layer is B, this layer is C, this layer is A again. So, what can you conclude? So, you can conclude that the distance between this sphere and this sphere is nothing but the body diagonal length of that face centered cubic unit cell. And we know very well the body diagonal length of any cube is root 3 into A. So, in the question what he is asking, the vertical distance, two vertically aligned spheres, what is the distance means? He is asking the body diagonal length in the unit cell, that is nothing but root 3A. So, our answer is root 3A. But what is A in a face centered cubic lattice? Right from cubic crystal systems I have been insisting to realize the relation between edge length and the radius. So, for this edge length and radius are A is equal to 2 root 2 R. A is equal to 2 root 2 R. R is given 4 angstrom units. So, A is equal to 2 root 2 into 4 angstroms. And our distance between the two spheres is root 3A. So, root 3 into A value is 2 root 2 into 4. So, you are going to get 8 into root 6. It is a very intellectually asked question. No need to break our head on this particular this height and spheres radius, nothing. Just take a smart correlation with face centered cubic lattice units. Actually, I would like to extend this question right now on the spot, like suppose I have got the ABC arrangement like this. This is CCP unit arrangement. There are 4 layers I am showing, A, B, C, again A. Suppose this distance is asked, how to work out between this sphere and this sphere, how to work out the distance. Again, if you take this arrangement and work out something, it will become very difficult. Rather, you take the unit cell and work out. Just now we have seen the unit cell. See, top face, left, right, back. So, 2 opposite triangles. So, I will take 2 opposite triangles. See, there is one sphere towards the front face and that sphere is towards back face. So, what is the distance between this and this means what? The front face center sphere, back face center sphere. So, he is asking the distance between the 2 faces. Distance between 2 faces is nothing but A. A is nothing but 2 root 2 R, or he has given 2 root 2 into 4 angstroms, as simple as this. So, like that, if you get any question out of this, you can easily calculate with reference to the face centered unit cell. That is a very good idea about this ABC arrangement versus the face centered cubic lattice, face centered cubic unit cell. So, this is a very easy method of solving such problems. What is the percentage of unoccupied edge length in a BCC unit cell of identical spheres? Assume body center atoms in contact with corner atoms. So, BCC unit cell, all are identical spheres. So, first get the picture. BCC means what? Corner atoms and body center atom. The body center atom. This is BCC unit cell. All are identical spheres. Identical spheres. Assume that body center atom in contact with corner atoms. Who are in contact? This body center atom is in contact with corner atoms. So, these 3 are in contact, they are in contact. So, obviously, these 4 are not in contact, they cannot. So, every corner atom is in contact with central atom, but the individual corner atoms are not in contact. And he gave this he gave one hint that all body diagonal is occupied by 4 radii, because they are all in contact. So, we can say root 3a, which is nothing but body diagonal length, will make 4 radii. Be very clear about it, because these 3 are in contact. Let me draw neatly. If you take a cube, let us draw only those ions, those spheres. See, there is a sphere here, here and here. See how many radii are there? This is one radius, another radius, another radius, another radius. There are 4 radius, which makes the root 3 of body diagonal, where the edge length is A. Keep it in mind. What is he asking? On the edge length, how much space is not occupied? So, if you take the edge of it, there are spheres in the corner, there is some space wasted. In that length, what is the wasted space, unoccupied space percentage? And we know A is how much? 4r by root 3. Edge length is 4r by root 3. This edge length, from this relation I got edge length to be 4r by root 3, out of which how much is occupied and how much is not occupied. So, if you take just one edge or one face, this is edge atom, this is edge atom. See, r and r, this is not occupied, a middle space length is not occupied. So, the occupied distance is just r plus r, 2r, and what is the total length? 4r by root 3. So, what is the unoccupied length? Length unoccupied is equal to 4r by root 3, which is total edge length, minus 2r, the occupied length. So, I am going to get r common, 4 by root 3 minus 2, that gives me r into 4 minus 2 root 3 by root 3. What is this part? Unoccupied part. He is asking the percentage unoccupied, means what? This unoccupied part divided by the total edge length into 100. So, r into 4 minus 2 root 3 by root 3 by total edge length. We know root 3 is equal to 4r. So, 4r by root 3 into 100. Try to understand, this is occupied, unoccupied part, this is occupied part. So, r and r get cancelled, root 3 get cancelled, 4 minus 2 root 3 by 4 into 100 is somewhere around 4 minus 1.7 into 2, 3.4 into 25. So, that gives me 0.6 into 25% unoccupied. So, whatever, that is only a numerical part left. So, here you should get the relation between A and R, and you should get R with the help of the body diagonal contact. So, such smart questions will be asked in solid state chemistry. The CCP lattice of oxide ions, all tetrahedral voids are occupied by some cation. What is the nearest cation distance? The nearest anion cation distance is given. In I think 4 problems ago we have done such problem, but not the same. There nearest anion distance is given, nearest cation distance asked in zinc sulphide. But here in a CCP lattice of oxide ions, all tetrahedral voids are occupied by cations. What is the nearest cation distance if the nearest anion cation distance is 2 angstroms? So, let us see. This is CCP unit cell. Every time you have to draw like this, safe corners, CCP unit cell, top face, bottom face, left face, right face, back face, front face. This is an oxide and all tetrahedral voids are occupied by some m plus x. Every tetrahedral void is occupied. So, where do you find the tetrahedral void? As I told you earlier, we will show it with this thing. These are the tetrahedral voids. They make a cube inside. See, if you connect, you can find. This. See, all are tetrahedral voids. These are all what? Cations. All cations. Now, what did he give? What is the nearest cation distance? In this lattice, what is the nearest cation distance? The edge length. The edge length in the inner cube, because they are all they are present in the tetrahedral void. All the tetrahedral voids inside FCC unit cell, you will have a cube. They are at the corners of a cube. In the cube, what is the nearest atoms? Corner atoms. So, he is indirectly asking the edge length of the inner cube. I told you very clearly, if the edge length of the outer cube is A, if the edge length of outer cube is A, automatically the edge length of the inner cube will become A by 2. A by 2. He wants nearest anion cation distance is 2 angstroms. First of all, where is the nearest anion cation distance? Nearest anion cation distance will be what? See, this corner is anion. Where is the cation? In the tetrahedral void. What is the distance between the corner and the tetrahedral void? Approximately 1/4 of the body diagonal. So, this 2 angstroms is anion cation distance, corner and the tetrahedral void distance. So, which is root 3a by 4. You have root 3a by 4. How much is this? 2 angstroms. So, what is A? 8 angstroms by root 3. From that, what distance do you want? Nearest cation distance, means this and this, which is nothing but A by 2. So, what will that be? A by 2 is equal to 8 by 2 root 3. To cancel 4. 4 by root 3 is our answer. 4 by root 3. That is a beautiful question you can enjoy. So, one should know that the tetrahedral voids make a cube inside, where the tetrahedral voids are present on the corners, and the edge length of that inner cube is the nearest cation distance, provided all tetrahedral voids are filled by cations. Be very clear. In the zinc sulphide problem what we have done earlier, the zinc atoms are present in the alternate position. They did not occupy all the tetrahedral voids. They have taken the alternate tetrahedral voids. So, 2 zinc atoms, 2 zinc ions are connected by a face diagonal of the inner cube, which is root 2 a by 2, that is a by root 2. But here the nearest distance between two cations is the edge length itself, that is a by 2 itself. So, be careful in solving such problems. So, this is how we work out the problems. Actually, let me tell you certain other things along with these problems. Suppose you have got a body centered cubic unit cell with all identical spheres. This is a body centered arrangement of close packed spheres. Suppose they ask a question like this: what is the first nearest distance between two spheres? What is the second nearest distance between two spheres? What is the third nearest distance between two spheres? A very interesting question. What is the nearest distance first of all in this? First nearest will be, see, the body center atom is in contact with every corner atom in BCC. So, what will be, let us assume the edge length is A. The first nearest distance will be what? Half of the body diagonal, because the body center atom is in contact with all the corner atoms. So, this is in contact with this sphere, that is the best possible nearest distance between two spheres, which is half of the body diagonal. So, body diagonal length is what? Root 3a, half of it by 2, that is the first nearest interatomic distance in any BCC unit cell made of identical spheres. What could be the next interatomic distance? Not from this, any between any two spheres. So, if you take this sphere and this sphere, whatever is the distance A is there, that is the second best distance. So, that will be what? A. What is the next possible nearest interatomic distance? You just see this face diagonal atoms will be the next possible nearest interatomic distance. There should be no atoms in between. See, these two are in contact, that is the best possible closeness between two atoms. So, I took it as half of the body diagonal. Then you have got the edge atoms, the next best interatomic distance, edge atoms, that makes A. The next best is face diagonal atoms, they are also not in, there is no atom in between. So, you can take it as interatomic distance. Face diagonal is what? Root 2a. So, what is the ratio? Root 3 by 2 is to 1 is to root 2. So, this is, if you multiply with 2, you will get root 3 is to 2 is to 2 root 2. This is the first interatomic distance, second interatomic distance, third interatomic distance ratio in a BCC. Now, let us analyze still a better aspect about BCC. The question is like this: one has to clearly understand the question. And this is a BCC unit cell. Now, the question is, from one particular atom, what is the nearest interatomic distance, what is the next nearest interatomic distance, what is the third nearest interatomic distance, in which case you have to be a bit more of working kind of a activity. See, what will be its immediate distance? This, which makes root 3 by root 3a by 2. What is the next nearest atom for this atom? He is not asking for any two interatomic distances. From one particular atom, what is the nearest distance, what is the next nearest distance, what is the next nearest distance. So, who is the next nearest atom for this? In this particular unit cell, all corners are at the same distance. So, you have to go to the next unit cell. There is a central atom. So, this will be the next nearest distance, because these 4 are at the same distance, the next nearest. Now, what is the distance? Between two body centers, actually you can draw one more cube like this. So, obviously you understand the between two body centers, the length is again this only, edge length only, because suppose you extend this like this, one more, this becomes body center, means what? Distance between two body center, successive body center atoms, body center spheres in a body centered cubic lattice will be nothing but A only. So, root 3a by 2 is the first nearest distance from a particular sphere, second nearest distance is nothing but A. What is the third nearest distance from this? That is a dangerous calculation. Generally students will be misled here. So, what is the third nearest sphere to this sphere? Most of the students will take it as these corner spheres, next unit cell corner spheres. Most of the students make that mistake. There is a better shorter distance than this. What is that? We have to be careful. If you take one unit cell like this, what is the third nearest? This is first nearest corner atom, the next body center atom is the second nearest. The third nearest is not the corner atoms, it will be the body center atom across the edge. This you have to take. Now, clearly tell me, from this, who is the first nearest? X. Who is the second nearest? Y. Who is the third nearest? This one, Z. Z. You have to go across the edge, not across the face and reach the other body diagonal, other unit cells corners. That will become fourth nearest, not the third nearest. So, if you draw a triangle like this, you will get a, what should I say, rectangle triangle, you can calculate this distance. So, this is A, this is A, and that is going to be root 2a. So, what is the nearest distance first? Root 3a by 2, that is x. From here, what is the next nearest? A, that is y. What is the next nearest? You have to travel through the edge. And here this is one body center, this is another body center. So, this is also A, this is A and this is A, and what will be the hypotenuse? This being A, this being A, this will be root 2A, A square plus A square under root 2 root 2, 2A square root 2 means root 2A. That is Z. That is the best, loveliest aspect of solid state chemistry. In the previous argument, we had the best 3 distances. Let you select any 2 spheres. But in this question, I am asking first nearest distance from one particular sphere, second nearest distance and third nearest distance. So, you have to be very careful in such solving such problems. And within this argument, we can conclude one more beautiful aspect. What is the coordination number of this sphere? 8, because every corner has a sphere. 8 is the coordination number. What is the second coordination number? Means other than these 8, what is the next best number? Next nearest neighbors. Where do you find? Here. Once you find a sphere in one cube, how will you get this sphere? You are travelling through this particular space. This has got, this unit cell has got 6 faces. So, from every face you will have 1 1 1. So, the first coordination number is 8, all corners. Second coordination number is 6, the body center atoms of the nearby unit cells, which you will come across the faces, 6 faces, so 6. What is the third nearest number of atoms? Just now we have calculated. Where do you find the third nearest atom? If you travel through the edge and you will find that. That is the third nearest atom. How many such atoms will you find? How did you travel to reach that sphere? Across the edge. How many such edges are there around this sphere? This being at the center of the cube has got 12 edges. If you travel like this across every edge, you will find such atom everywhere. Therefore, you will get 12 such atoms which you meet when you travel through 12 edges from this body center atom. So, the third nearest are 12. First coordination number is 8, second coordination number is 6, third coordination number is 12. I am still interested to know the fourth coordination number. Next to this, which spheres are the nearest? Obviously, the next corner spheres. How many such spheres will you come across around this? You are travelling across one face. How are you meeting these 4 spheres? You are travelling across this face. 1, 2, 3, 4. 4 spheres on one face, but you have got 6 faces to this unit cell. So, if you travel across one face, you are seeing 4 spheres. When you are travelling across 6 spheres, 6 faces, 6 fours are 24 spheres. 8 is the first coordination number, 6 is second nearest, 12 is third nearest, 24 the fourth nearest. So, like this there is no limit in solid state chemistry. If you observe carefully, we have just discussed about only cubic system. If you assume all the 7 varieties of systems, how much scope will be there to study solid state chemistry. And one particular solid is adopting, how do you know that rock salt adopts that kind of a structure, how to know it? We have got X-ray diffraction techniques to understand the structures of crystals. We have got Bragg's equation. Through X-ray diffraction we will understand interplanar distances and how many varieties of interplanar distances are there and what are the ratios of those distances. Once you know, from that ratios of the interplanar distances we can correlate the crystal structure to one particular variety of the unit cell. However, in our next class, having done so much, we have thoroughly done everything, every parameter we touched, number of spheres, number of nearest neighbors, second nearest neighbor, third nearest neighbor, closest distance, second closest distance, third closest distance, and cation, anion, cation distances, so much we have done in the form of problems. Next thing is going to be the defects in the crystals. The crystals will never be ideal. So, whatever we have discussed may not be exactly the same structures adopted by all crystals, there will always be defects like this. There will be defective crystals only. Defects are natural. Defects are natural. There will always be some defects when a crystal is formed. Some planes will be missing sometimes some ions will be missing, some places one ion will be dislocated, some line of ions may be missing. So, they are all called defective crystals. A crystal is formed, then defect is not generated, while crystallizing itself defect generates naturally. So, we will enjoy the defects. Sometimes we will put defects in the crystal, that is also a beautiful aspect for some good purpose. Now that we are enjoying so much electronic media and all because of some defective crystals. So, defects are good. Let us enjoy how the defects are classified in our next lecture. So, keep watching all the past classes also until you get used to the crystal structures. We will meet in the next class. Thank you.